Welcome to the session, Divide and Conquer, Master GPU Partitioning and Visualize Savings with OpenCost. My name is Kaysie. I'm a product manager on the Azure Kubernetes service team at Microsoft. I work on everything cost management and optimization, so really excited to talk about this topic with you. Unfortunately, my co-presenter and colleague, Ali, wasn't able to make it today, so it's just me. All right, so today we'll chat a bit about why people are even running GPUs, what this looks like in the industry. We'll layer in costs. So when we think about GPUs and costs, what are some of the challenges and issues that we're facing? And then we'll talk about how to monitor GPU usage metrics, visualize your GPU costs, and then ultimately implement partitioning techniques to go and optimize your GPU utilization. And we'll tie it together in the end with a demo showing how to set up NVIDIA GPU Operator, implement time slicing, and then also leverage OpenCost. So as we all know, GPUs are scarce and expensive. The scarcity often means that when we get a GPU, we may want to hold on to it, even if we're not using it. And if we're doing that, if we have a GPU, we want to make sure we're extracting every penny, every cent out of it that we can because they're so expensive. So really, why do we want to pay for these GPUs if they're not going to be utilized and they're sitting there idle? GPU utilization, this is the amount of time during which one or more kernels are executing on the GPU. And by default, when Kubernetes is scheduling GPU workloads, it assigns a whole GPU to a single workload or job exclusively. This is called exclusive access. And with Kubernetes, in the pod manifest, when you're actually requesting your GPU resource, you have to request in whole integers. So it's a little bit of a different model compared to CPUs where you can request fractions of a CPU. The exclusive access model means that usually a workload is not going to use the entire GPU's resources. So a lot of the utilization is actually going to be sitting there idle. This means, when we think about at scale, is this actually feasible? Is it economical to run AI workloads on GPUs? Well, it absolutely can be if we, implement certain strategies. But before we talk about the strategies, let's take a look at some data. So in a recent Gartner peer survey of over 500 tech leaders, they found that over 48% of organizations are actually using Kubernetes already to run their AI ML workloads. For AI and LLMs, Kubernetes really is the ideal platform to be running these workloads. Why? Because Kubernetes provides scalability, elasticity, the ability to scale up and down automatically based on resource demand is definitely a huge advantage, especially for training or apps that require massive amounts of compute. Kubernetes is declarative by nature, so we communicate upfront how much resources our workloads require, and then Kubernetes will handle all that scheduling, which really reduces the operational overhead and burden that typical operations teams might experience. And lastly, Kubernetes is dynamic and flexible. Containerizing your AI apps means that you can, there's increased extensibility and portability. You can run your AI apps across clouds, on public, on-prem, even in hybrid scenarios. So let's dig into GPUs more. How are they different from CPUs? Fundamentally, they are doing different things because of how they're architected and built. CPUs are ubiquitous. There isn't a single digital device that doesn't have them. CPUs are more general purpose too. They're fast and versatile, so they can handle really complex processes with varied instructions, versus GPUs are much more specialized. They're specialized processing units, really optimized for performance, parallel processing, throughput, running thousands of operations at once, concurrently, even if they are repetitive operations. And additionally, CPU processes are serialized, whereas GPUs processes run concurrently. So if a GPU is given a task, it'll subdivide it into thousands of smaller tasks and then process them at the same time concurrently. Now let's look at some common use cases in industry. GPUs, since they're so suitable for handling large processes made up of different parts, they really excel at like scientific calculation, computationally complex algorithms, inferencing, training, image processing, and they're used across many different industries and verticals as well, from healthcare to gaming to FinServe, you name it. But as I mentioned before, GPUs are expensive and costs can balloon really quickly. So if I look at my infra or cloud bill at the end of the day and see how much my GPUs actually cost me, I might get that sticker shock, and this is how I might feel. This is not fine. Oh my gosh, why are things on fire? Why are my costs so expensive? What is my problem? So how can we go from this to this new mentality of it's fine, everything will be fine because my costs are now under control? So let's see how we can get there. Three steps that we'll walk through today. So monitoring your GPU costs with NVIDIA DCGM Exporter. Second, visualizing GPU costs with OpenCost. And then finally, optimizing your costs. You can do that through right-sizing your infrastructure, but we'll be talking about partitioning techniques. So monitoring GPU metrics. The NVIDIA DC GPU Manager, DCGM for short, is a suite of tools for managing and monitoring your NVIDIA GPU clusters and DC environments. It provides health monitoring, comprehensive diagnostics, system alerts, governance policies, and a whole bunch of great telemetry metrics. The DCGM really is the foundation for a lot of GPU monitoring capabilities. And the DCGM also integrates into the Kubernetes ecosystem through the DCGM Exporter, which provides GPU telemetry in containerized environments. So the exporter will essentially expose GPU metrics at a HTTP metrics endpoint. And this means you can really seamlessly integrate into other monitoring or visualization tools, open source tools as well, like Prometheus and Grafana. And you can run the DCGM exporter as a standalone container. You can also deploy it via the NVIDIA GPU Operator. And the GPU Operator is really great. It's a tool that kind of automates the life cycle of the software and manages the software required to use GPUs with Kubernetes. It also manages, configures, provisions GPUs to scale like other resources in a Kubernetes cluster. The exporter also has some really great metrics to help expose over or underutilization, as well as GPU node health. So let's take a look at some of these metrics. Here we have just the out-of-box Grafana dashboard that is directly integrated and pulling metrics from the DCGM exporter. This is great. It's a standard out-of-box metrics, and we see a whole plethora of different telemetry. Specifically, I can see my GPU utilization not looking too good right now. 0% utilization means it's not being utilized well, but I'm still having to pay for this expensive GPU. Not great. I can also see memory utilization percentage, memory allocation, temperature. Again, a whole different metrics to understand how efficient my GPU currently is. In this case, clearly not very efficient. Here's another view, a different set of metrics. We see GPU power usage, power total, GPU temperature. All are quite important metrics to monitor regularly to help you evaluate and respond to utilization trends, anomalies, to fine-tune and optimize your performance. Now that we have monitoring in place, we've seen our GPU metrics, let's actually visualize the costs. So here we can use OpenCost. OpenCost is an open source vendor-neutral CNCF project. Actually, just 2 or 3 weeks ago, it was promoted from CNCF Sandbox to incubation, which is quite exciting for the whole community. I know we have some folks in the community here as part of OpenCost. OpenCost essentially provides a standardization and spec for measuring, reporting, allocating, and even visualizing your cluster infrastructure costs across cloud environments. And with OpenCost, you can really nicely slice and dice your cluster costs by Kubernetes abstractions like namespace, labels, containers, any Kubernetes construct, essentially. And we'll take a look at this in a demo pretty shortly, how we can see costs with the OpenCost API. So we have monitoring, visibility in place, and our third final step is optimizing the costs. GPU cost optimization is really about maximizing your GPU efficiency while reducing the total cost of ownership for your GPU infrastructure, but without compromising on performance. So you may think that selecting the most powerful GPU or the largest GPU instance type is the best, but this isn't always the case. This often leads to unnecessary costs, underutilized resources. So right-sizing your GPU infrastructure is quite important so that you can balance your workloads needs in terms of memory, processing power, et cetera. You can do this manually. You can also leverage Carpenter, which is an open source project as well, to pick the most cost-effective SKU for your GPU based on your workloads requirements, which is great. And cloud providers also offer quite a broad range of GPU options, from the entry-level ones that are better for running small inferencing workloads or smaller models, all the way to higher-end GPUs, which are great for large-scale training or large amounts of data processing. And then you can also leverage partitioning techniques to combat underutilization and actually split up your GPU and share it across multiple workloads. So NVIDIA supports several partitioning techniques to oversubscribe your GPUs. Oversubscription is kind of like carpooling, where you're packing more people or processes, in this case, into a single car, or a GPU in this case, to make it being used more efficiently. GPU partitioning can happen at the application level. It can also happen at the software and hardware levels. So let's specifically look at the three in the middle, so time slicing, MIGs, and MPS. Time slicing, this is the simplest approach. This provides you the ability to run several workloads concurrently on the same GPU, rather than having them spread out across multiple GPUs like in the dedicated model up top. Each process will be alternating in execution time in a round-robin fashion. And for each of the duration of the time slice, they have full access to the GPU. And then once the time slice is completed, the GPU will be relinquished and then allocated to the next process in the queue. When you are basically defining time slicing in your config, you'll define a set of replicas that you want for your GPU. So in this case, since I have 3 dedicated GPUs, for example, I want my time slice GPU to have 3 replicas, and each slice will be handed out independently to a pod to run the workload on it. Another cool thing about time slicing is that you can apply it to specific nodes in your cluster. It doesn't have to be all the nodes in your cluster. So for example, I can apply time slicing just to my Tesla T4 GPU nodes only, and not to my A100, or if there's specific GPU nodes that are running specific processes, they don't have to be time sliced as well. And one caveat to call out about time slicing, because each slice has full access to the GPU, there's not really a control over how much or how many resources a process can request. So if one process is requesting a large amount of resources, it could lead to kills or issues or other performance-related issues for the processes that are running in succession. So that's just one caveat, is that there can be some unpredictable performance here. And then we have MPS, multiprocessing service. This is a method of space partitioning. Here, each workload will remain resident on the GPU, but it won't be swapped out in terms of execution time, like in the time slicing model. And here, each fraction only uses a portion of the GPU's memory and compute capabilities, since it is logically partitioned. So we don't quite have the same unpredictable performance like we did in the time slicing model. And then MIGS, our last partition technique, this enables a single GPU to be partitioned into separate GPU instances, up to 7 instances, and each are secure and isolated at the hardware level from each other. So this is really great for multi-tenanted use cases. It's similar to MPS in that the resources on the GPU are space partitioned, but each partition will get a dedicated portion of the GPU's computational resources, memory, so each can run independently without interruption from the others, possibly due to lack of resources. So this is the best strategy for a more predictable performance, if that is important. And you can also combine strategies. So you can combine MIGS and time slicing, for example. Within a MIGS partition, you can further leverage time slicing within a single partition. So it's great that you can kind of combine strategies to tailor to your scenarios. And now we have a demo. So this demo will have 3 parts. First, we'll create a Kubernetes cluster, set it up with a standard node pool, as well as a GPU node pool with the GPU operator enabled. And then second, we'll install Prometheus and OpenCost and show the OpenCost API and how we can look at our GPU costs. And then third, we'll implement a time slicing GPU and show how simple it can be to get set up with that. All right, so here we are in our CLI. I'm creating a standard AKS cluster. It'll have a node count of 1 just for this demo purpose. I'm going to create a namespace and deploy a very basic web app. And then soon we'll see all of my Kubernetes resources being created. So this is a very straightforward, normal, basic setup for a CPU node. Then here I'm creating a second node pool. In this node pool, there'll be 1 GPU node, standard NC4AS GPU, and I'm going to actually skip the GPU driver install because we'll see in a later step that with AKS at least, the driver will be automatically installed by default with the GPU operator. And then I will add NVIDIA repo update, and then I can finally install the NVIDIA GPU operator. And now looking at my nodes, I can see my GPU node is up and running. If I describe this node, I'll see the various drivers, device plugins, DCGM, exporter. They've all been deployed as part of the GPU operator. And then I can just go ahead and deploy my sample application, my GPU demo app. There'll be a few, this is just a batch job, and there'll be a few runs that are happening. If I check out the logs here, we'll see that there were 500 runs for this app that was using 1 GPU for its computation. And if we dig into some of the details, we'll see the name up there, Tesla T4 was the GPU, and we can see other details like total and free memory. So that was our first kind of basic setup. And now I want to look at my GPU costs. So first, we'll need to install Prometheus. And then we can go ahead and Helm install OpenCost. Very quick and simple. And once the OpenCost pod is ready, we can just port forward. Now, if I go over to my browser, we're going to be looking at the OpenCost allocations API. So OpenCost does actually have a UI, but some of their GPU metrics and GPU cost capabilities are just available via API at the moment, which is still great. You can programmatically pull this data into whatever visualization analysis pipeline you have kind of built, whether that's Power BI or Prometheus Grafana, something else. But the allocations API, this allows you to query for cost and resources allocated to Kubernetes workloads based on on-demand pricing by default. You can configure your own custom specific pricing or integrate into cloud provider cost APIs, but out of box, this is the experience I'll show, is just the on-demand pricing. So within this API too, you specify a lookback window. I specified the last 7 days, and then my aggregation is at the namespace level. But like I mentioned before, you can aggregate any Kubernetes primitive. I can look per container, per deployment, per service. But here I've just chosen per namespace. And my resolution window is 1 minute, which is just the duration that is used for Prometheus queries. So more frequent queries of Prometheus just means higher accuracy. And here we'll take a look at a few of our namespaces. Let me go to the GPU namespace. There we go, our GPU app namespace. We can see details about the controller kind was a job. We see details about what the node SKU type was, NC4AS, like we had set up. And then since my job had just run for a few short minutes, the cost and utilization data was actually quite low for my GPU. For example, it just ran for 3 minutes. I can see how much the average CPU request was, how much CPU was actually used, and how that translates into a CPU cost. And then similarly on the GPU side, I can see that I requested 1 GPU, but what I actually used on the GPU was a tiny fraction. Here, GPU cost is based on your real GPU utilization, not based on your GPU requests. So even though the cost here seems very small for this job and this namespace, I still am actually paying for the entire GPU, even though it's not being utilized right now. So that delta in this marginal cost versus the price tag that I see on my bill, that's opportunity to save and to close that gap. All right, and finally, let's take a look at implementing GPU partitioning, specifically time slicing. So in our cluster, we had our regular CPU node pool, our GPU node pool, and now we're going to create a GPU time slicing node pool. Again, it'll just have 1 node. We'll skip GPU driver install again, and same NC4AS node type. Once this is up and running, let's check our node. Not quite ready yet, but that's okay. We will look at our GPU operator pod. And for this new node, there are actually several new containers that are running. So the DCGM exporter, device plugin, driver daemon set, these are all being initialized as part of the GPU operator that we had installed previously. And then we'll just take a look at our namespaces. And before we apply the time slicing config, I just want to show what the config actually looks like. So I'm just applying this to the single GPU time slice node. You can specify for A100s, for example, your time slicing and MIGS partitioning technique, or kind of like how you want to set that up. But since I don't have any A100s, this config won't apply. But on the bottom, I do have a section for Tesla T4. In my config, I specify I want to split my Tesla T4 GPU into 4 replicas. So it's pretty simple how you actually define how many replicas you want. I will apply this time slicing config. And then one more step. We have to patch the cluster policy, device plugin config name. And then our GPU time slice node is ready to go. We'll just add a label to it. And then finally, we can describe that node And there we go. We see in the capacity and allocatable, now we actually have 4 NVIDIA GPUs, even though we've only provisioned a single GPU in the initial setup. And we can also see the device plugin label that we had set for Tesla T4. And now we can go and deploy and apply our sample application. So this job YAML, the main difference between the time-sliced version and the non-time-sliced application is that in the spec, I've defined parallelism, 3 concurrent jobs to be run, and completion, I want 3 jobs to be completed. And then again, the limit is the same thing, just the limit of 1 GPU. And when we go and apply that, the same process will happen. We can see that those jobs were completed. Check out the logs, and it looks almost the same, pretty much the same as my non-time-sliced GPU. However, with the time-slicing model, I could run more workloads on this GPU, different sizes, different amounts of resources, and this is different than my non-time-sliced GPU, where this wouldn't have even been possible. So just wanted to show how quick and easy it is to get up and running with time slicing. And some of our final key takeaways. So GPUs are expensive, but they can be feasible and economical to run if you implement some of these techniques. Monitoring and visibility is key because without these utilization metrics or cost metrics, we don't know what is being underutilized. We don't know where to focus our efforts and keep teams accountable for their GPU spend. Exclusive access for a GPU is the default, so implementing partitioning is just one method to help us optimize our GPUs, but it can really help improve utilization and reduce costs. Some additional details about the partitioning techniques. So time slicing, best for apps that are not latency sensitive or that can tolerate jitter. MIGs, best running multiple apps in parallel, but very important if they need to be resilient and have high quads, then MIGs is a great option. And then finally, MTS, best for running apps in parallel that can maybe deal with some amount of limited resiliency. So that is all. Thank you so much, and I hope you have a great end of your KubeCon. Thank you. All right. Thank you.
So OpenCost only accounts for the cloud provider's instance cost, right? So there needs to be some more calculation to correlate to the slice of the GPU if you wanted to do that kind of level of financial accounting.
Yes.
Have you thought about how far you're going to go? I mean, in the end, you end up with like how much did it cost per token, presumably?
Mm-hmm. Yeah, I know that there are some efforts on the OpenCost side to kind of explore supporting costs in the time slice model. Right now, it's more focused on the exclusive GPU and reporting those costs. But yeah, definitely time slicing is an area that is being explored. And would definitely love to collaborate, see how we can make that happen.
Yeah, it's very cool. Thanks.
That was exactly, so yeah, we are trying to make that work. So if anybody's interested, like Kaysie said, that's an area that myself and Alex from KubeCost are looking to make sure that OpenCost supports that. So any participation from the Microsoft side would be great as well. We're looking to make that story better. The second question that I have is, the last time I had a chat with you and Bob about the OpenCost add-on on AKS, we found out that it's not pushing to Prometheus, but it's writing to a file-based thing. The downside for us is that when we install a product on top of the add-on, we can access the OpenCost data, So we'd have to like uninstall that and install OpenCost because that, we can't simply access the underlying mechanism, right? Is there going to be any changes to that to either push it to Prometheus or give access to the file that you guys are putting the raw OpenCost data?
That's not something that we are, well, it's something that we can definitely explore. At the moment, we haven't exposed the OpenCost metrics to Prometheus in the native add-on just because of how we're doing reconciliation with the Azure cost data. It's a little bit of a different process than how OpenCost does reconciliation, but definitely we can explore if that makes sense.
Yeah, 100%, because it results in a better customer experience. And by the way, great presentation. I know Ali was on there. You did a great job.
Thank you.